Hey everyone, so we're going to be going through this exam 2 review today, and I posted these solutions already, and so I am going to probably skip over some of the details, some of like the integration by parts and stuff like that. I'll just kind of skip because those things you can just kind of go over to Husky CT and look at those on your own time. And we're just going to kind of focus on the main ideas, and I might expand on certain ideas that maybe they don't show up exactly in this exam review, but they're still like fair game for the exam or something like that. So I'll skip some details and then spend more time on other things that I think are important. So in problem 1, we're trying to find all solutions to a boundary value problem. Remember that boundary value problems can either have a unique solution, they could have infinitely many solutions, or they could have no solutions. Right, and so in this problem, we begin by finding the characteristic equation and then finding the roots of that. So this would be plus or minus I, and so the roots lead to the general solution y equals c1 cosine x plus c2 sine of x. We need to plug in these boundary values, which involve y prime. So we'll start by taking that derivative and then plugging in our values to determine what c1 and c2 should be. So y prime of 0, this is negative c1 times sine of 0, which is 0, and then c2 times cosine of 0, which is 1, and this has to equal 1, and so we get that c2 is equal to 1. Okay. Second thing we need is for y prime of pi to equal 0. And so y prime of pi, this is c1 sine of pi plus c2, which is equal to 1. We just figured that out. And then times, or plugging into y prime, so this would be cosine of pi. Remember that cosine of pi on the unit circle, that's over here, so this is a x value of negative 1. And so this right here is just negative 1 times 1. And so we get c1 times 0 minus 1 equals 0, or negative 1 equals 0, which is impossible. And so there's no pair c1, c2 such that this function with those choices of c1 and c2 will satisfy both of the boundary conditions given. And so there's no, this is not a eigenfunction problem. This is just a boundary value problem, so there's no solutions here. Oops. So no solutions in this. All right, so there's no solutions in this thing. The next one is an eigenvalue and eigenfunction problem. I was kind of getting ahead of myself. So this guy, you might have noticed if you looked at an early version of this that the second condition used to be just y prime of pi equals 0. And the reason I changed that is because with the y prime of pi equals 0, this was literally just the quiz question that you guys had to do. And so I changed the boundary condition to just give you guys a different problem to do. All right. So, so our differential equation has characteristic equation m squared plus lambda equals 0. And so the roots of that would be plus minus the square root of negative lambda. And so this leads into the 3 possible cases for what our general solution could look like, and depending on whether lambda is positive, negative, or 0. And so the first case that I'll do here is lambda equals 0. So in this case, your DE is y double prime plus 0 equals 0. So I'll just write that as y double prime equals 0. And what's the general solution for y double prime equals 0? Well, we're just looking for a function whose second derivative is 0, and linear functions are exactly those. So y equals c1x plus c2 would be our general solution here. And by the way, I'm okay with you guys kind of jumping to the general solutions for most of these things, because what, like, all three cases, like lambda equals 0, lambda greater, or lambda less than 0, all of them, their general solutions are like pretty common, and so I'm okay with you guys just jumping to the general solutions given whatever the case is. So our conditions, one of them involves y prime, which in this case is just c1. So the condition y prime of 0 equals 0 tells us that c1 equals 0, because that's what y prime of anything is. It's equal to c1. The other condition is y of pi equals 0, and that tells us that c1 pi plus c2 equals 0. But c1 we know to be 0. And so this tells us that c2 is 0, and so y equals 0 is the only solution here, and our eigenfunctions are not allowed to be 0, and so there's no solutions other than the 0 solution, or the 0 function that satisfies the DE and the boundary conditions, right? If you were to get that, like, y equals like c1x like satisfies the boundary conditions, then those would be your boundary functions. If you found that like y equals c2 satisfies the boundary conditions and the DE, then those would be your eigenfunctions here. We only have y equals 0, and so there's no non-trivial eigenfunctions. And lambda equals 0 is not an eigenvalue. The next case we'll handle is lambda, let's do lambda less than 0. Yeah, let's do lambda less than 0 first. So here, this is m, right? So m equals plus minus square root of negative lambda. Negative lambda, because lambda itself is already negative, this is a double negative, and so negative lambda is positive. Right? Just like flipping the sign, you're flipping the equation as well, right? Or the inequality. And so this gives us two real roots, and so you could do like the c1 e to the like mx, m1x plus like c2 e to the m2x like as your general solution, or you could jump to the other solution. So this is like y double prime plus lambda y equals 0, and when lambda is positive, the general solution to this, we talked in class about y c1, I'll do cosh, c1 cosh of our m value times x plus c2 sinh of our m value times x is our general solution. Okay, and this is basically just because the second derivative of cosh would just be itself, but then each time that you take a derivative, the chain rule pops out like a square root of negative lambda. So the first derivative of this would be square root negative lambda times cosh, and then the second derivative, I'll put the c1 there, and then like the second derivative would be like c1 times negative lambda. Oh, sorry, that should have been sinh. Derivative of cosh is sinh, and then the derivative of sinh is cosh. So this one over here would be square root negative lambda times cosh, square root negative lambda x. I'm kind of rambling here, apologize, but yeah, like if you like keep taking these derivatives or whatever, like for example, like basically what I'm trying to say here is like if you plug this guy or this guy into the differential equation, the second derivative would be negative lambda times this guy. And so if you, so y double prime would be negative lambda times cosh, and then y is just cosh. And so negative lambda cosh times plus y, or lambda times cosh, those cancel out, and so it does in fact give you 0. Okay, anyway, not talking about like why this satisfies the differential equation. We're here, we have the general solution, and so let's now check the boundary conditions to see if there's any non-trivial solutions. So we need y prime of 0 equals 0, and then y of pi equals 0, right? So y prime of 0 equals 0, and y of pi equals 0. So this one right here tells us that c1 negative square root negative lambda sinh of 0 plus c2 square root negative lambda cosh of 0. This has to equal 0. Sinh of 0 is equal to 0 in the same way that sine of 0 is 0, and then cosh of 0 is equal to 1 in the same way that cosine of 0 is equal to 1. And so this tells us that c2 times some constant is equal to 0. And remember that this is a non-zero value, and that tells us that c2 itself must be 0. All right, so only way to satisfy this is for c2 to equal 0. And then the other condition we need is y of pi to equal 0. And so this tells us that c1 cosh of pi plus c2 sinh of pi has to equal 0. But then c2 is 0, so this term just goes away. Sinh of pi is not equal to 0. Like, this is just some non-zero value. We don't care or know what it is, but when you multiply it by 0, it just goes away anyway. So we get c1 times cosh is equal to 0. But cosh is only equal to 0. Sorry, cosh is always greater than or equal to 1. Graph looks like this, and in particular, it's never equal to 0, right? And so that tells us that c1 has to equal 0. And so y just has to be the trivial function here, so there's no eigenvalues or eigenfunctions here. And then our last case would be if lambda is negative. So we get y double prime minus lambda y equals 0. And so the general solution here is going to be c1 cosine of square root lambda times x plus c2 sine of square root lambda times x. By the way, you might be wondering, like, why is this like a square root lambda, and like we had like a square root of like negative lambda up here? Well, basically we're how you can kind of try to remember this is that if lambda is positive, then square root of lambda is a real number, so you do want to have a real number in here. And if lambda is negative, then square root of negative lambda would be a real number, because you'd have to flip the sign before you take a square root, right? So that's sort of what's happening here. And then when you, like, why does the negative kind of disappear here? Well, your characteristic equation, sorry, that should have been plus. I don't know why I had a minus there. But the characteristic equation is m squared plus lambda equals 0, m equals plus minus square root of negative lambda. And if lambda is a negative value, then you can write this as I times the square root of lambda, like just positive lambda, right? So this is sorry, this is assuming that lambda is a positive number, though. I'm kind of getting ahead. We already did the negative lambda. Sorry, I'm like a little scrambled right now, I guess. All right, but just to say the correct thing, case 3 is that lambda is greater than 0. And so this is what leads to this case right here. So if lambda is positive, then m squared plus lambda has roots plus or minus square root of negative lambda. And if lambda is positive, then this would now be a negative value. So you can factor out the I from it. And then this leads to your general solution with sine and cosine instead of cosh and sinh. All right, y prime is c1, negative c1 times square root lambda sine of root lambda x, and then plus c2 square root lambda cosine of root lambda x. And so now we'll plug in our conditions. Y prime of 0 equals 0. I think that was the right condition. Yeah, y prime of 0 equals 0. So this leads to negative c1 times root lambda times sine of 0 plus c2 root lambda times cosine 0 equals 0. This goes away because sine of 0 is 0. And then cosine 0 is 1, so we get c2 times square root lambda is equal to 0. Lambda is a positive value, and in particular, it's not equal to 0, so that tells us that c2 has to equal 0. Our other condition is that y of pi equals 0, which tells us that c1 cosine pi plus c2 sine of pi equals 0. C2 is equal to 0. Sine of pi is also equal to 0, so this is very 0. And then cosine of pi is equal to negative 1. Okay. Wait. Sorry, I screwed up. I didn't plug into this correctly because I forgot the square root of lambda. All right, let me plug that in correctly. I'm just gonna copy paste this real quick. And then just replace the x's with pi's. That's what we get when we plug in. The reason I had like red flags in my head was that we were searching for what lambda should be, and because I didn't have any lambdas in my equation, then that was kind of a red flag that something was off, and then I might have plugged in wrong or something like that. So if your lambdas just kind of like disappear or something like that, then maybe you plugged in wrong. Did I do that correctly up here? Yeah, it looks like I did that wrong up here too. But so let's maybe fix that real quick. So this should have been like square root negative lambda times pi. This should have been also square root negative lambda times pi. But the logic still stays the same. Cosh of square root negative lambda times pi is greater than or equal to 1, and this still doesn't matter. This is just always a non-zero value, and so we still get the same conclusion. So nothing really affected us up there. But it will affect us down here. So, all right, so we have our condition. We already know that c2 of pi is equal to 0. We know that c2 is equal to 0. And so even though we don't know what sine of root lambda times pi is equal to, it doesn't matter because that whole term is just going to be 0 anyway. So we need that c1 cosine of root lambda times pi is equal to 0. And remember, what we're searching for is non-trivial solutions. So if c1 was equal to 0, then that would tell us that our function y is equal to 0, and that would not be helpful. We're looking for non-trivial solutions to this. And so if we don't want c1 to equal 0, then what we would want is for cosine to equal 0. So we want cosine of root lambda pi to equal 0. And when does cosine of some value equal 0? So on the unit circle, cosine gives you the x values and y gives you, sine gives you the y values. And so the places where the x values are 0 are up here at 0, 1, and down here at 0, -1. And those happen at the angles pi halves and 3 pi halves. But also you could have these values plus like any multiple of 2 pi. So like plus 2n pi, this plus 2n pi. Or you could just combine all of this into one set of information just by saying it's going to be pi halves plus any multiple of pi. Because pi halves plus pi brings you down here, plus another pi brings you back up here, another pi, and then every time you add pi, it just takes you either to the North Pole or to the South Pole. So what we need is for our angle to equal pi halves plus n pi, and our angle is root lambda pi. So this has to equal pi halves plus n pi. We could divide both sides by pi, and this gives us a half plus n. And I'll simplify that to, this is like 2n over 2. Okay? And so then we can write this as 2n plus 1 over 2 equals square root lambda. And so lambda is equal to 2n plus 1 over 2 squared. And this is for n equals, let's see, can n be 0 here? Yeah, so this is for, yeah, n could equal 0 here. So 0, 1, 2, 3, so on. Because remember, we're in the case where lambda is positive. So any value of n that gives you 0, or that gives you like something non-zero here would work out just fine. You could do like negative values of n here as well, but then that would give you repeats in your list, and so you might as well just throw out the repeats. And then y is equal to, so remember C2 is 0, so this is equal to y, right? But let's get rid of the C2 part. That part is 0. So y is equal to this, but then when we plug in our value of lambda, we get C1 times cosine of square root of something squared. That goes away, and so you get 2n plus 1 over 2 times x. This is for n equals 0, 1, 2, 3, and so on. By the way, the negative values of n would not give you any issues up here because you're squaring stuff. If you take the square root of, like, if you did have a negative value of n over here, then you take the square root of it, I guess taking the square root of something squared, you technically want like absolute values on that. Although cosine is an even function, so the negative wouldn't really matter anyway, so you just you still get the repeats, but I don't know, it's not that important. All right, so that's enough time on that. All right, let's get to Fourier series. All right, so finding the Fourier cosine series for the function on the interval 0 to 4. This is going to be the part where I start not really doing all the details, right? So remember that a cosine series is when you write your function as a0 over 2 plus the sum from 1 to infinity of an times cosine of n pi x over L. And here our L is the length of this interval, which is 4. Okay. So we're basically just writing this guy as a sum of cosine functions. All right, and so the formula that you should remember is that an is equal to, for cosine series, is equal to 2 over L times the integral from 0 to L of f of x times cosine of n pi x over L dx. As a note, let's see, how do I want to say this? Maybe I'll come back to that, the note. Basically, I was going to talk about like the formula 1 over L times negative L to L of what, same thing inside this. I'll just say it here, I guess. People get kind of confused like when to use like the first one versus the second one. When you're doing Fourier cosine series or a Fourier sine series, you pretty much always want to use the 2 over L times the integral from 0 to L1. There's like almost no situation where you would ever want to use this one, because if your function is already known to be an even function, then technically this thing over here would work. But if it already works, if you already have an even function, then this, because of the properties of even functions, even odd functions, I guess, then this integral would be equal to this integral. And so, and this integral is easier to do because one of the bounds is a 0 as opposed to having like a negative in there. So this integral is just easier to do if f is an if f is an even function. If f is not an even function, this formula is not even valid and would give you something totally different from like what you actually want. It would give you basically the half of like the Fourier series for the function without the sine part. And so you would end up just not be, you'd be computing something, but like it's just not the Fourier cosine series. So if f is not even, this formula doesn't work. And if f is even, this formula is equal to that one. So for Fourier cosine series, you should always, pretty much always be using this one. For Fourier sine series, you should always be doing the one with, this is like bn, but then this is sine. Same logic, like this one would technically work if f is odd for sine functions, but it would be equal to like this guy. So just do the one with the, just do the easier one. Now that said, when you get to just regular Fourier series, that logic, that is no longer necessarily true. When you get to regular Fourier series, you actually don't want to do these. So for Fourier series, so this is the side, so I'm just gonna like go on this tangent here. So for just a regular Fourier series, so like you're representing a function as a0 over 2 plus the sum of an cosine n pi x over L plus the sum of bn, sorry, n equals 1 to infinity, bn sine of n pi x over L. So here, an is equal to 1 over L times the integral from negative L to L of fx cosine n pi x over L dx, and then bn is 1 over L times negative L to L fx sine of n pi x over L dx. Now, if your function is not odd and not even, then you are basically just required to use these formulas for your coefficients a n and b n. By the way, remember that your a0, the n equals 0 term, gets typically this integral gets computed separately, but it's the same formula. However, if your function is known to be like an even function or known to be an odd function, then you can basically use some tricks to make these replace one of these integrals with like the corresponding one up here. So like if your function is if f is like definitely going to be an odd function, then that means that a Fourier series for the function like would literally just be a Fourier sine series, and all of like the a-n's would just disappear. And conversely, if f is even, then all of your b-n's would be equal to 0, and then these guys would not be 0. And you can compute the a-n's by doing the 2 over L times integral from 0 to L thing. So if you know that your function is even or odd, then you can basically cut all of this work in half by only having to do the computations for the a-n's or only do the computations for the b-n's. So like on one of the quizzes, a lot of people, I think one of the quizzes, like the function was like f of x equals like 3x or something like that. So like if you needed to get the Fourier series for 3x, what you really should be doing here is noticing that this is an odd function. And so if it's an odd function, then all of your a-n's are going to be 0 for all n. This symbol right here means for all. So all of your a-n's are going to be equal to 0. And so the only thing you need to calculate is the b-n's, which is the integral from 1 over L, negative L to L, times 3x sine of n pi x over L dx. Right? And then furthermore, because it's odd, this would be equal to 2 over L times the integral from 0 to L times 3x sine of n pi x over L dx. And so you can just kind of shorten that work by like a lot by doing this. And so like yes, you can like go through the computation yourself and like check that like this integral is equal to 0 like every single time, or you could not do that and just save yourself like half of the work that goes into that whole like integration by parts thing, because like this integral right here like would kind of suck to do like 3 different times or whatever, when you could just do it once. All right. Anyway, that's enough of a tangent. At this point, I'm just going to kind of go through the actual problem. Now that I've talked generally about it all. So, all right. So if we're getting the Fourier cosine series for this piecewise function, so we know our L is equal to 4. So we'll use this formula, but replace L with 4 in all cases. 4, 4, 4. And then we just need to replace F with what it's equal to. And now in this case, because F is a piecewise function, you want to split this integral up into an integral from 0 to 2 and then an integral from 2 to 4. By the way, this is a half over here, so we're going to just write that as a half. And then we get a half times the integral from 0 to 2, and then plus distributing the half to both integrals, a half times the integral from 2 to 4. And from 0 to 2, f of x is just equal to x. And then from 2 to 4, f is equal to 2 minus x. By the way, this is all for n greater than 0. You do typically want to handle the n equals 0 case separately. So A0 would just be cosine of 0 pi x over 4 in here. So that's literally just cosine of 0. So this would just be 1/2 times the integral from 0 to 2 of x, and then plus 1/2 times the integral from 2 to 4 of 2 minus x dx, because cosine of 0 is 1. And so this would give you, well, the integral of 1/2 x is 1 over 4 x squared. And then if I distribute this, this becomes 1 minus 1/2 x. And so this guy over here becomes x minus 1/4 x squared. And then that's from 2 to 4. And then you plug in your values here. So this would be 4 over 4 is 1 minus 0. And then plus 4 minus 16 over 4. And then minus, plug in 2 minus 4 over 4, which is 1. And so you get 1 plus 0 minus 1, which just ends up being 0 in this case. Okay, so yeah, your A0 ends up being 0 in that case. If it ended up being 5, just remember that when you plug it into like your final answer, that first coefficient, like you need to divide it by 2. So like if this was like a 5, then your final answer, you'd have 5 over 2 and then plus some other stuff. All right. And then anyway, I'm not going to do these integrals over here, but you'll just do like integration by parts on each of them. So this guy would be like u equals x. Your dv is cosine of n pi x over 4. And so your v would be 4 over n pi times sine n pi x over 4. And then your du would just be 1. And then you do like a similar thing over here. And then when you do all of that, you should end up getting that your an is equal to, I'm just going to copy my solutions over here. It's pretty rough. 4 over n pi sine of n pi over 2 plus 8 over n squared pi squared times 2 cosine of n pi halves minus 1 minus negative 1 to the n. Okay, and so f of x is equal to a0 over 2, which technically is like 0 over 2. I wouldn't typically write that. I'm just kind of being a teacher right now. And then plus the sum from 1 to infinity of, and then you just kind of copy your coefficients down here. Boop. And then times cosine of n pi x over 4. Okay, I'm actually going to erase that. All right, and so that's how you do it. The graphs, so just start off with like the graph of the function. Looks crooked. Yeah, there we go. All right, so the function is equal to x for 0 to 2. And it's a closed hole here and an open hole here because of how it's defined. And then it's equal to, and then it looks like this from 2 to 4. Closed hole and then open hole. That's just the graph of y equals 2 minus x. You plug in x equals 2, starts at y equals 0. And then plug in x equals 4, ends up at y equals negative 2. So your y value up here is 2, y value down here is negative 2. So this is f of x. And then you draw the even extension from there. And then the even extension is going to look like something like this. good enough. That. Boop, boop, boop. Yeah, so even extension just makes it symmetric about the y-axis, so you're just doing a horizontal reflection like so, right? Like there's a mirror. And then the Fourier cosine series says take the even extension of this guy. Okay, I'm going to get rid of the closed holes because the values at the discontinuity points are going to be important. So let's do this. Just do it again. Okay, so these open holes are lining up, and so those are actually not going to be discontinuities. Okay, that's fine. All right, and then at the discontinuities, the actual function that the Fourier series or the Fourier cosine series will converge to, the value of it will be halfway between those two open holes. So there, 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 and there. Okay, and so if our y value is 2 up here, and then 0 there, negative 2 down there, so when you like do this copy paste sort of thing to get your periodic extension, these points right here line up, so you don't get any discontinuities there, right? But then these points over here, there's already a discontinuity there, and so we do get those discontinuities, and the values of those discontinuities is just going to be halfway between 0 and 2. So our discontinuities is discontinuous at x equals, all right, so that was 2. Oh, I didn't mean to copy paste all these 2's there. But remember our period is 4, so this is 2, 4, 6. This would be like 8, and then 10. This would be 14, 18. So it's like we're at x equals, this is negative 2. So this is like 2 plus like any multiple of 4. So 2 plus 4k. And then the value at each 2 plus 4k is L equals 1. All right, let's start going a little bit faster here. How are we doing on time? Oh, this is already getting really long. Oh well. All right, so that was Fourier sine series. No, that was Fourier cosine series. Oh my god, we're only on problem 4. Jesus. All right. Great. All right. All right, I've kind of laid down a lot of the foundation though, so this one we'll probably do a little bit faster. So this one, like all the work is like very much similar. It's just going to be a difference in, like, it's the same function, right? Same exact function. And so let's actually, just because we already kind of have the graphs here, let's do the graph of what it's going to converge to first, just because that's kind of where my train of thought is right now. And so the first thing that we'll do here, because this is the Fourier sine series, remember sine is an odd function, so we're going to get the odd extension of this guy. So odd, we reflect this guy about the origin, so 180-degree rotation, which you can also think of as do a rotation horizontally and then vertically, like across the y-axis and then the x-axis. And then do the same thing over here. Across the y-axis would give you this, and then across the x-axis would give you this. And so we'll get Come on. Odd extension looks like this. And then if I care about the holes, looks like that, and then that. All right. So this is our odd extension. And from here, let's get rid of these holes here. There. Come on. There we go. All right, and now copy paste that to get our periodic extension of this. One more time. This looks weird. Why is this like off? Oh, is this yeah. Copy paste that one more time. Should be good. Okay, it's just not really lining up with this thing super well, but it's close enough. All right. Anyway, you're just kind of copy pasting this picture, right? And so we can see like discontinuities here and then here. That should be an open hole. And here. And then these just kind of keep repeating. All right, so here's like -2, here's +2, and then this is 4, 6, 8, 10, 12, 14, 16, 18. All right, so here's how you want to think of this. So this is so the length of like our interval is 4. But the period of this function is not going to be 4. The period of this function is 8 because we're going from -4 to +4, right? So we're taking this interval and then we double the length of that. So now that length is 8. And so the period will be 8. And so we're going to get our discontinuity points in our original interval, -4 to 4, and then take those discontinuity points and then just add multiples of the period to get that. And so our discontinuities happen at -2, at +2, and then also at 4. So we'll get -2 plus 8k. We'll get 2 plus 8k, and then we'll get 4 plus 8k. It's also like going to be a discontinuity like over here at like -4, but that would fall under the category of like 4 plus or minus 8k. So these are going to be our discontinuous points. So we're discontinuous at these points here. So -2 plus multiples of the period, +2 plus multiples of the period, and then 4 plus multiples of the period. And then our values at these points are going to be halfway between the left and right limits at those points. So at -2 plus 8k, so remember this y value here is -2. This y value up here is +2. So at -2 plus 8k, halfway between 0 and -2 is -1. At 2 plus 8k, it's going to be halfway between 0 and +2, which is L equals 1. And at 4 plus 8k, it's going to be halfway between 2 and -2, which is 0. So those would be the values of the discontinuities there. All right. And then as far as computing the coefficients for the Fourier series, for the Fourier sine series, Bn is going to be 2 over L times the integral, and then L is 4 in this case, right? We're going from -4 to 4, L is 4. And then we integrate from 0 to 4, fx times sine n pi x over 4 dx. You don't have to do like an n equals 0 case, and this is for, there's no n equals 0 term here. This is for n greater than or equal to 1, right? And then so this would be like 1/2 times the integral from 0 to 2, and then times x. And then plus 1/2 times the integral from 2 to 4 times 2 minus x. I think that's the other function. Yeah, 2 minus x times sine n pi x over 4. And then you compute the coefficients much in the same way that they are computed for the Fourier cosine series. And then here, the bn's end up being a lot nicer, ends up as -2 over n pi. And, oh wait, sorry, I'm looking at the wrong thing. No, they're not much nicer. they're actually quite bad. 4 over n pi times -1 to the n minus cosine of n pi over 2 plus 16 over n squared pi squared sine of n pi over 2. And then the Fourier series would just be f of x equals sum from 1 to infinity of these coefficients, which I'll just copy paste, times sine of n pi x over L, which is 4. All right, cool. Question 5. Is just finding a Fourier series for this function here. So here, we make it periodic with period 4, but then we're going from -2 to 0, and then 0 to 2. So in this case, this is not an odd function, it's not an even function, and so you have to use the formulas an equals 1 over L, integral from -L to L, f of x cosine n pi x over L. And then Bn is same thing, but with signs. Crap. -L to L. And you know what, let's replace our L's with what they are. L is 2 in this case, so -2 to 2. And then fx sine n pi x over 2. Make that a 2 as well. All right, so in this case, so your a0 is just going to be 1/2 integral from -2 to 2 of f of x times cosine of 0. And so this is 1/2 integral -2 to 0 of just 2 dx, and then plus 1/2 0 to 2 of x dx. All right, and so 2's cancel, integral of 1 is just x, and then this gives you 1/4 x squared, 0 to 2, and then this should end up being equal to 3, I believe. I'll just do the integral, 1 minus -2 plus 1/4 of 4 minus 0, so that's 2 plus 1 is 3, so that's your a0. All right, and then your an for n greater than or equal to 1. Again, just use this formula and then split it up into 2 integrals with 2 and an x in there. This one comes out, so I'll just give you the answer over here, and you can check the details on the posted solutions. And then your Bn comes out to be -2/n⁻, like so. And so f of x ends up being, so a0 is 3, so you do 3/2, and then plus the sum from 1 to infinity of an times cosine n⁻x/2, and then plus the sum from 1 to infinity of bn times sine of n⁻x/2, like so. So that's the Fourier series. And then to graph it, so from -2 to 2, or to 0 rather, is just equal to the function f of x equals 2. Oh no, the solutions I posted, I didn't do the graph. Oh well, I'll fix that. Okay, so from -2 to 2, it's equal to 2, and then from 0 to 2, it's equal to x. So it looks like that, and it looks like that. Copy, paste that. I'll put it down here, I guess, because we're about to take a periodic extension. By the way, where's the domains? Less than or equal to, and less than, so it would be like here, and then open, and then close, and then open. But then over here, when we take our periodic extension, yeah, good enough. Okay, cool. So, okay, so in this case, our periodic extension is only going to be discontinuous at 0 right here, and that's because the endpoints actually line up, assuming I'm reading the function correctly. Yeah, so the endpoints are lining up, and so we don't like create any new discontinuities by like not matching up the endpoints or anything. So our only discontinuities are really going to be coming from copy pasting like this center point discontinuity over and over again. So over here we get that, over here we get this, and so this is going to be our Fourier series. There's no like odd or even extensions to do with this guy. It's going to be discontinuous at 0 plus multiples of the period. The period is 4, so 0 plus 4k. You could just write 4k if you want, doesn't matter. And then the Fourier series converges to L equals 1 there. Okay. All right. All right, question 6. This one is just straight up in the notes. It's just kind of there to tell you guys that this is something you should know how to do. This is just a derivation of the Fourier sine series coefficients. And so I'll mostly skim through this. So the idea is you start with the equation fx equals sum of bn sine of n⁻x over L. And then what you do is for a fixed m, So m is fixed here. Then you'll multiply by sine of m pi x over L on both sides. And then we're going to integrate. So once you do that, then you integrate both sides with respect to x. And you're integrating from negative L to L. And then right at this point, there's sort of a subtlety that happens where you can switch the integral and the sum. And so here, you're, instead of integrating an infinite sum, you're taking an infinite sum of all of these integrals. So you can just compute all of these integrals one by one, and then add up the values of all of those. And this is by the Fabini-Tonelli theorem. So that's like important part number one. Well, I guess the main important part is this like first step right here that you want to multiply and then integrate. And then from there, all of these integrals are either equal to either 0 or ignoring the bn. If I like factor out like the bn from there, it's equal to 0 or L, depending on if n is not equal to m or if n is equal to m. So remember that m is like a fixed value, and so for like n equals 1, like if m is like 7, then like this whole thing would be 0. For n equals 2, it's 0. For n equals 3, 4, 5, and 6, it's 0. And then once you get to n equals 7, at that point, it's going to be b sub 7, or b sub m in general, times L. And so that's what that thing is equal to. And then so we get that, and then you just divide both sides by L, and then you get your formula for b sub m. It's 1 over L, negative L to L, fx sine m pi x over L. The problem asks for it like with like n's instead of m's, but like it's just a different letter. It doesn't really matter. Okay. So yeah, that's sort of the idea behind that. All right. Question 7 is just separation of variables. Just checking whether or not they're separable, and then if they are separable, separate it. So for t u x x plus x u sub t equals 0. So here, the assumption that you want to make is that u of xt is a product x of little x times capital T of little t. And then for shorthand, we'll just write that as capital X times capital T. And so in this case, uxx, this just means take a partial derivative with respect to x twice. So that's going to give you x double prime times t, because t is like remaining constant in this case. And then like u sub t, this is, you're taking a partial derivative with respect to t, and then keeping x constant. So this would be like x times t prime. And so our differential equation here is going to become little t times x prime prime capital T plus little x times capital X t prime. By the way, please make sure your lowercase and capital x's look different from each other. Otherwise, like, things might go screwy for you. The grader might not know what you mean. I grade the exams, but like, yeah, just make sure that like what you're writing is legible. This has to equal 0. And now we'll separate the variables if we can. So let's bring this term to the left, or to the right. And then we'll divide by the x terms and on both sides, and then divide by the t terms on both sides. So this becomes x prime prime over negative little x capital X equals t prime over little t capital T. Okay, and then so at this point, because this is only involving x's and this is only involving t's, what we discussed in class is that these both have to be equal to the same fixed constant. This is because if x is allowed to stay constant and t is allowed to like change freely, well, for like any fixed x, you can plug in whatever t value you want and it's going to be equal to like whatever this thing is, which is being held constant, right? And then vice versa. So they both have to equal some constant lambda. So we get two equations. We get that t prime over little t capital T is lambda, and then same over here, x double prime divided by negative little x capital X equals lambda. And then we'll simplify, we'll multiply through, and then we get negative lambda little x capital X, and then add that to the left side, and then boom, we've got our ODE, like so. And then do that over here as well. T prime equals lambda little t capital T, and then subtract that over, equals 0, and then boom, you're done. Okay. By the way, you could call this separation constant. Like you could make this separation constant negative lambda. You could make it like probably not lambda squared because that would imply that it's positive, but you could call it lambda, you could call it negative lambda, you could call it 5 lambda, whatever you want. It just has to be like something that represents all fixed constants, all possible fixed constants. I went with lambda here because it didn't really matter, because these things are just gonna, you know, be reasonably nice looking regardless and not have any like negatives in there. Now, if you look at the other one, I believe that one's not going to be separable. So this one's like uxx plus x plus y uyy equals 0. So in this case, our function is of x and y. So we'll write u as capital X times capital Y, or like capital X of little x times capital Y of little y. And so when we plug this into the DE, we get x prime prime y plus little x plus little y times x y prime prime equals 0. And you'll see with this one, you just kind of get stuck. So x prime prime y, like you could try distributing these terms over here. And I just don't think there's a way to like you can't like let's see, if you were to try to man, what would you even try? Like I guess you could like try like dividing by like x on both sides, like so x double prime y over x plus like x plus y double prime equals 0, and then maybe try dividing by y. This is like almost separated, and you could like bring this to the right hand side. You're just gonna get stuck because of like this little x plus little y thing over here. So even if like you get like all the x's by themselves, like kind of like, I don't know, you just can't right here. So this is just not separable. So this is not like a proof or anything like that. Yeah, this one just can't really do it. So like on an exam, if I were like trying to like test you on that, like I could like say like, all right, one of these two things is separable, figure out which one is separable, or maybe like I say 2 out of the 3 is separable, or determine how many out of the following are separable, and then separate the equations if you can. I don't know, something like that. 8 and 9 are just like wave and heat equation ones. So this one right here, find a solution to the following problem. So this one right here, this equation is literally the wave equation, or sorry, the heat equation. And so the heat equation, you'll be given the solution to the heat equation and the solution to the wave equation on the exam, but you should be able to recognize like that, like, oh, this is the heat equation, or the wave equation looks like the other thing, or whatever. Like you should be able to like tell the differences between those. And if I tell you what, if I like write down sum n equals 1 to infinity cn e to the negative n squared pi squared alpha squared over L squared T sine n pi x over L. Like if I like give you this right here, you should know that this thing is for the heat equation. And the wave equation would be like if this was like sine of n pi a t over L. Like that would be like the solution for the wave equation. So you should like, if I tell you those, you should be able to recognize which one is used for what, basically. Okay, so these are the solutions to like the heat equation. This is what they look like, where Cn is equal to 2 over L times the integral from 0 to L fx sine n pi x over L dx. Now, what's important about the CNs? So the CNs is the thing that you like need to solve for, but what's important about them is not that they're equal to this integral right here. What is important to them about them is that these are the like what is this formula for? This formula is the formula for the coefficients of a Fourier sine series of this function up here. Oops. Can I just copy that? Yeah. Yeah, it's literally just the coefficients of this Fourier sine series right over here. Okay. But what is a Fourier sine series? A Fourier sine series is writing this function as a sum from 1 to infinity of Cn times sine of n pi x over L. In this case, L is given to be 10. This is like the L is like showing up in all these places, right? So L is 10 in these cases. And so we're writing sine of pi x over 10 plus 4 sine of 3 pi x over 10 minus 5 sine of 6 pi x over 10. We're writing this as a sum of like constant times sine of n pi x over 10. But it's literally already written as a Fourier sine series. Like this is the Fourier sine series of itself because it's already written as a like sum of sine functions. And so this tells us like this right here, this is the n equals 1 term because sine of 1 pi x over 10, right? This right here is the n equals 3 term, right? Because this is sine of 3 pi x over 10. And this right here is the n equals 6 term. This is sine of 6 pi x over 10. And so this tells us that c sub 1 is equal to the coefficient, which is 1, and then c sub 3, that's the coefficient of this guy, that is equal to 4. And then c sub 6, the coefficient of the n equals 6 term, is equal to negative 5. And then c2, c0, or there is no c0, c2, c4, c like 5, c7, etc. All other cn's are equal to 0, right? So these are the only non-zero coefficients. And so u of xt, which equals this, let's copy that, bring that down here. Let's actually replace the L's and the alphas in the proper way. So L is 10, so L squared is 100. This is 10. What was alpha? Okay, yeah, this is alpha is 2 in this case, so alpha squared is 4. Yeah, so we get this, but then for n equals 1, c sub 1 is 1, right? So we get 1 times e to the negative 1 squared. I'm going to put that 4 in front. So this is 4 times 1 squared times pi squared over 100 times t, and then sine of 1 pi x over 10, right? And then the n equals 2 term, that coefficient is 0, right? So we won't even write that one. And then the n equals 3 term, that coefficient is 4. And so we'll get negative 4 times n squared, which is 16, and then pi squared over 100 times t. And then sine of, this is the n equals, wait, did I screw up? Yeah, I screwed up. Wrong thing over here. This is n squared right here. So n squared, and this is the n equals 3 term right here. This is the n equals 1 term, this is the n equals 3 term. So I'm going to replace this with 3 squared right here. So n squared is 9 in this case. Okay. So we get negative 4 times 9 pi squared over 100, and then sine of, so n is 3, so this would be 3 pi x over 10, and then plus our coefficient for n equals 6 is negative 5, and then e to the negative 4 times n, which is 36, pi squared over 100 times t, and then times sine of n is 6 pi x over 10. And so you get that. Of course, you could simplify this a little bit if you wanted to. You don't have to. I don't particularly care to. Here you can kind of see like, oh, n is 1, so 1 shows up there. N is 3, so 3 shows up there and there. N is 6, so 6 shows up there and there. And then the coefficients just kind of go in front of all these things. So this would be the solution. Okay. And then finally, let's do the last one. So this one just kind of ends up being an integral. So wave equation 1. All right, so we got a string of length 6. The ends are being held fixed. The string is set in motion with no initial velocity from an initial position given by this function here. And we want to find the displacement and assume that a is equal to 1 in the wave equation. And so the wave equation solutions, and you should be able to recognize that this is a solution to the wave equation, not the heat equation, and then vice versa. So this is sine n pi x over L times cosine n pi a t over L. And then Cn is given by 2 over L integral 0 to L fx times sine n pi x over L. So these are just, again, the coefficients of the Fourier sine series for this function. And this function is very much not a sine function or written in a Fourier sine series. And so this one, we very much have to like actually do the computation of these integrals right here. So in the previous one, this is kind of there to like give you a hint that like, oh, it's for the Fourier sine series. And this one, this is just computation. So what is our L in this case, and what is our A? So A is equal to 1, so I'm just going to delete the A out of that thing. So A is 1. Oh god, just wanted to move the T. Just erase it and put it over there. And then L is 6 in this case, so because we're going from 0 to 6. Oh, it just tells us L is 6. Great. Okay, and then down here again, L is 6. Boom, boom, boom. Okay. All right, so let's compute. So 1 over 3 times the integral of fx sine n pi x over 6 dx. So this is 1 over 3 times the integral from 0 to 2, plus the integral from 2 to 4, plus the integral from 4 to 6. And then we just replace f with what it's equal to on each of these integrals. And so this one's pretty straightforward because on the first one is just 0. On the second one is just 5. And then it's always like times sine of n pi x over L, right? But I'm not writing it for the other ones because it just gets zeroed out. And then this guy is just going to be 0 again, right? So this guy and this guy go away, and then all you have to do is, so I'll write that as like 5/3, and then times the integral from 2 to 4 of sine of n pi x over 6 dx. So this one's actually pretty quick to do. And so you integrate, this is going to give you 6 over n pi times negative cosine of n pi x over 6 from 2 to 4. And you just plug in your bounds. This and this cancel to a 2, so we get negative 10 over n pi for our coefficient out there. And then plug in those bounds, you get cosine of 4 over 6, which is 2 over 3 times n pi. And then minus cosine of, oh, sorry, I forgot the n. Yeah, so x is 4 over here, so this becomes n pi 4 over 6. So I'll write that as 2n pi. And then when we plug in 2, this becomes n pi 2 over 3. So n pi 2 over 6, which becomes n pi over 3, like so. And so these are our coefficients. Cn, and so u of xt is equal to the sum from n equals 1 to infinity of these coefficients, which I'll just shrink, and then times sine of n pi x over 6 times cosine of n pi t over 6. And this is just using this up here. So I'm just replacing the Cn with what we just calculated it to be, and then just the rest of it is just sort of part of the formula. Okay, so those are your solutions. So you don't have to memorize this formula right here. You don't have to memorize the formula for the heat equation, but you should be familiar with like, oh, well, if you see like 4uxx equals u sub t, this is the heat equation. And then what does the wave equation look like? This would be where you have, oh, sorry, this should have been like alpha squared. The wave equation is like a squared uxx equals u, and then there's like a second derivative, u sub t. And like one way you can kind of like remember that this one is for the wave equation is because there's a second derivative here, and so we need to specify not just the initial position, but we also need to specify the initial velocity in addition to the initial position. So like that's why like the wave equation is like we tell you, oh, there's no initial velocity. The initial velocity is 0, and the reason we do that is because this is like a second derivative with respect to t, and then a first derivative with respect to t leads to us only needing to specify the initial position, just with like, you know, sort of initial condition stuff with or initial value problem kind of stuff. All right, so that's enough rambling. Sorry if this kind of like took a little longer than it needed to, but hope that this helped. All right, good luck studying, guys.